Morning, everyone. Okay, we'll get started in just a few minutes. A few reminders on the slide here about these last couple weeks. So, homework 11, the suggested due date is today. There's just one more homework, which is homework 12, and that's up now, due next week. The last lab is this Thursday. I should have that online by the end of the day. And then the last assignment will be the final project. So this is going to go out on the last day of class next week. You'll have a full week to work on this project. You don't have to pick a 48-hour window. You can work on it at any time you want during that week. And that'll be due on May 7th. So thanks for filling out the survey. The overwhelming response was that people would like a class that's focused specifically on how we can use some of the techniques in this class to address the current pandemic. And so I'll be putting stuff together for that class. That'll be on the 30th. Again, it's optional, so it's not going to be tested on the final project at all. But if you're interested, please tune in. You can also ask questions. If you have specific questions ahead of time, you could also send them in. I'm going to try to focus on stuff that's specific to this class. But yeah, I could also try to address other things people have questions about. Okay. So for this week, we're going to talk about something that's a little bit different from the rest of the content of the class. And this is a different way of thinking about what the goals of our statistical analyses should be, and a different way of thinking about how we should report understanding evidence from experiments. Oh yeah, there's a question in chat about lab solutions. That's a good reminder. Let me double check. I think there's at least one I haven't put up yet that I should from the last couple weeks. And then I'll definitely make sure all of those are up before the final project goes out. Okay, so if we think back all the way to when we first started talking about probabilities, we talked about probabilities as being kind of the population version of just a average frequency, right? So we could, in any sample, we can count up how many times some event happened and divide by n to get a proportion. And this is something we're measuring in our sample. And a probability is just kind of the population version of that, right? Which is the long-term average. So this way of thinking about probability is called the frequentist kind of probability, right? Which means that we're just counting up frequencies of something happening. And if we have many, many trials, we can approximate what the probability of this thing happening is. So this makes sense for lots of things, lots of kinds of probabilities that we do, right? We usually use like a rolling a die example or something. But there's also other kinds of probabilities that we talk about that don't really fit into this kind of frequentist framework of counting up multiple outcomes from the same kind of trial. So for example, we might hear people use probability to talk about future events. So, right, we might have some model that's making a prediction that says something like the probability of more than 3.5 degrees of warming overall on the globe, but by 2100 is 39%, right? And so this is a probability that I think people could make sense of, right? It's sort of talking about how likely we think some outcome is, but it's not really clear how this would fit in the counting frequencies kind of definition, right? So this is something that hasn't happened yet, and it's only going to happen once, right? Eventually we are going to be in the year 2100, but it's not like a population we can sample from. And we don't have any samples from it yet, right? So it's not really clear that this is some kind of average frequency. People could also make these kinds of statements about the past, right? So we could say there's a 90% probability that Amelia Earhart crashed on a specific island, right? And so this is again, this doesn't really make sense as a frequency because this is a single event that either happened or it didn't. And we don't know if it happened or it didn't. And this probability here is just about our beliefs based on the evidence that we have. There's a question in chat about whether P's are descriptive or inferential, right? And so probabilities are always an inference, right? Because probabilities are a property of the population. They're something that we can't see. And so we've talked about one way of estimating this probability is with a proportion, right? We can measure a proportion in a sample. And so, yeah, and the notation here is also kind of confusing that we use the symbol p both for proportions and for probabilities. So we have to be a little careful. The p on this side is a population probability. The p on this side is a sample proportion, right? But so these kinds of things here, these are definitely inferences, right? These kinds of probabilities are definitely inferences, but it's not really clear that they're like frequencies in a population. We can also have probabilities that change as we learn more things. So, for example, there's this great movie, The King of Kong. It's a documentary about these people competing for the world championship in Donkey Kong. And part of the storyline is that there's some doubt about whether one of the entries is legitimate or not. And so initially this high scoring Donkey Kong run is ruled as the new world record, but then more evidence is collected, and then the probability that this is a genuine score gets lower and lower as people review the evidence. And so right, this is talking about probabilities here that are actually changing as a function of what certain people know, right? So the person that was faking this tape presumably already knew whether it's real or not. But right, this is talking about probabilities that are held by particular people based on particular information that they have. And so this kind of way of talking about probability is really about what a certain person's belief is in something based on the evidence that they have seen. And one reason thinking about probability in this way might be good as a scientist is that what we really want to be able to say is, after we conduct our experiment, say something like the probability that our hypothesis is true is 87% or something, right? This is maybe what we'd like to be able to get out of our experiments is, based on the data we have so far, what's the chance that a certain hypothesis is how the world really works? Right. And remember, this is not what p-values are, right? And we'll talk about that more throughout the lecture today, right? But remember that p-values are where we assume a particular hypothesis, right? Usually the null hypothesis, and ask how likely the data is under that particular hypothesis, which is not the same as the probability that the hypothesis is true, right? And so this Bayesian approach is, let's try to actually answer this question about the probability of our hypothesis, because this is really, at the end of the day, probably what we care about. So this way of thinking about probability is referred to as Bayesian probability or Bayesian statistics. And the idea is that probabilities can reflect our beliefs about the world, and it can be about things about the way the world currently is, or things that have happened in the past, or predictions about the future. And these probabilities are not going to be just counts of things that are happening, but they're going to be sort of our most updated version of our beliefs about what's happening. And every time we get new data, we can update these beliefs. And so this kind of approach, in many ways, is kind of a backlash against the null hypothesis methods we've been talking about for the rest of the class. That instead of getting these p-values, which again is the probability of our data assuming that the null hypothesis is true, instead what we should be doing is we have some probability of this null hypothesis, maybe a probability of some alternative hypothesis that we actually care about. And what we want to know is, based on the experiment we ran, how should we adjust our beliefs, right? Should we trust our hypothesis more than we did before, or less, and by how much? And what happens if we do multiple experiments, right? How should we adjust these things? Another way this is a backlash against null hypothesis testing is that we don't just decide to reject or fail to reject, right? We really want to have this sort of continuous probability from 0 to 1 of how much we believe in some hypothesis. And so we don't need to have a specific cutoff. We're not going to say, we don't have to ever accept or reject any hypothesis, right? We can just have multiple hypotheses. We have the probability of each of them, and then it's changing over time. And the sort of iterative nature of this is also important, right? And so the logic here is that there's going to be kind of a cycle where we start with some kind of prior guess, we make some predictions about what our data should look like. Then we actually collect our data and look to see whether our data matches our predictions. And we can use that to update our knowledge. And this new updated knowledge now becomes our prior knowledge for the next version of this cycle, right? This guy in the middle here is Thomas Bayes, who this is named after. Right. So the idea is that we repeatedly do this first deductive process of making predictions on our data. And then we use our data to do this inductive process of updating our knowledge. And so this cycle can just keep going, right? We just can keep designing experiments that are going to give us useful data in order to improve our knowledge of which hypotheses are true. Okay, let's do a quick quiz here. So the reason to use Bayesian statistics is to A, decide whether to reject the null hypothesis, B, update the probability of hypotheses based on data, C, compute more accurate p-values, or D, avoid specifying an alternative hypothesis. Okay, so what is our goal with Bayesian statistics? All right. Yep. So yeah, I'm seeing lots of B's. Yeah, we're not computing more accurate p-values exactly, although we're sort of computing something that's more useful than a p-value, maybe, right? We're computing like the actual probability that we want instead of a traditional p-value. Okay, so what we want to get is from our Bayesian statistics is something like, what's the probability of some population parameter given our data? And so we're going to write this as p of theta given x. This theta is just a stand-in for anything. So it could be a mean, a variance, a median, whatever, right? There's something in the world that we want to know about. That's our theta. And we have some data x, and we want to know based on this data x, so assuming this x data that we collected is true, then what does that tell us about the probability distribution of this thing we care about in the world? Right. So we'll do a bunch of examples with different things here, but this theta, you could often think about it as like the mean of our population that we're taking samples from, or this could also be something like in a nominal case, it could be something like the probability of different nominal outcomes in the population. So this is our goals, is we want to figure out based on some data, what are our beliefs about something about the population. So what we've been doing so far with p-values is computing something else, right? Which is the probability of that we would have gotten data this extreme, assuming that our null hypothesis is true, right? And so what we want to do with this Bayesian version is different from the previous version in two ways, right? The first is that instead of just thinking about this null model, we're going to think potentially about a whole like family of models that have different population parameters. So for example, instead of just a null model where the population mean is 0, we're going to imagine that the population mean could take lots of different values. It could be 0, but it could be plus and minus 1 and 2 and 3 and right. It could be any value in between, right? And so instead of just this in p-value world, we only have this one model that we care about, which is the null model. Here, we're basically this theta here is sort of like a continuous parameter, and so we could think about the population having any mean potentially, right? So this is one thing, is we're going from a single model to potentially many models, right? We'd have at least two with like a null model and an alternative, but we could potentially have a whole like continuous family of models. And the second thing we need to do is we need to get this conditional probability in the right direction, right? That in p-value world, we assume some model. So we assume that the population mean is 0, and look at how likely the data is. Now we want to do the opposite. We want to say, we're going to assume this data is true. What does that tell us about the probability that the population mean is 0, or that the population mean is 1, right? Or whatever, or all these different values of theta. So we're just going to do a small bit of math here to think about how to flip around conditional probabilities. So let's go back to the definition of what a conditional probability is. So the probability of x given theta, when we talked about this a few weeks ago, is just the probability of x and theta divided by the probability of theta, right? That all we do is this conditional probability basically just means that we renormalize this joint probability of both of these things by the probability of this thing we're assuming, right? So this is just writing down our definition of p of x given theta. And so what about p of theta given x? So if we write down the definition of this, the numerator is the same thing. It's just the joint probability of x and theta being true at the same time. The denominator is just different, right? We're normalizing by a different thing here. And so if we we have this term here that's the same in both of these. So if we just multiply this one by this p of theta, we multiply this one by p of x, we get that these two things have to be equal to each other, right? So when we, this joint probability of x and theta, we can write it as p of theta given x times p of x, or p of x given theta times p of theta, right? I'm just taking these two equations and looking at the two different ways of writing this joint probability. So then if we just divide by one of these, like this p of x, for example, we end up with the form of this that's referred to as Bayes' rule, right? And so again, this Bayes' rule just comes directly from the definitions of conditional probabilities. And right, what this has in here is it shows us a connection between p of theta given x and p of x given theta. So we're going to pretty much spend the rest of the class today trying to understand what this equation means and try to get some intuition for what it means. And so there's a bunch of different terms here. So and they also have different names. So so just to remember what the goal here, right, is what we want is, given our data x, we want to say something about some population parameter theta, which again could be like the population mean or anything else that we're trying to learn about the world. And so Bayes' rule says that there's sort of three ingredients here. So there's this thing, which is called the prior. And so this p of theta, this is p of theta that's not conditioned on our data x. This is what our beliefs about this population parameter were before we ran our experiment, right? So that's why it's called the prior. It's our belief that's before we run the experiment, right? How likely do we think each possible value of this population parameter is? Then there's some of these terms in the middle that depend on x. And these terms are basically about the evidence. And we'll also call this term the likelihood later on. Right. And so this here is like, it's kind of like a regular p-value. At least it's the same direction as a regular p-value, which is for each possible assumption about what the world could look like. Right. So we're going to make some assumption here of what the population parameter is. How likely is the data under that assumption? Right. And so so these conditions, and then we'll talk about this denominator term later. We're going to mostly ignore this term today, right? But the point is that these are the terms here that depend on our data, and they basically tell us how likely we think it is that we could have gotten this data under each of these possible hypotheses about the population parameter theta. And so Bayes' rule tells us that if we multiply these things together, so we start with our prior, then we multiply our evidence, what we end up with is this thing called the posterior on the left here, right? And the posterior is our distribution of beliefs about this population parameter theta conditioned on our data x, right? And so Bayes' rule basically tells us how we can go. This is sort of a formula for how we're going to go around this circle of incorporating new information into our beliefs, right? What we do is we take our beliefs before the experiment, then we're going to reweight our beliefs based on what's happening in the data. And then now we have a new set of beliefs that now have incorporated this data that we've seen. Right, so this is an updating procedure that tells us how we can get a more and more precise distribution of what's going on in the world by adding in new pieces of evidence. Right, and another important thing here is that this posterior can then become the prior for our next experiment. Right, this is just sort of telling us how we update our beliefs based on some new piece of data. And these posteriors are kind of relatively easy to interpret, right? These are again, going to be distributions, probability distributions over what we think the world might look like based on our data. And again, so this posterior here is not what a p-value is, right? A p-value is more like this term up here, which, and the p-value is specifically just about the null model, right? Which is if we have this, whatever the theta parameter is that corresponds to our null model, what's the chance of getting our data out of that null model? And so, right, this is one of the fundamental differences with this Bayesian approach, is that we always have to start with a prior. This is both a sort of a feature and a bug of Bayesian analysis, right? That in most of the stuff we've done so far, we don't have to say ahead of time, but before we run this analysis, we don't have to say whether we believe the null hypothesis or not, or how likely we think it is. And so, so in the Bayesian setup, right, we're kind of saying that this isn't really true, right? That before we run the experiment, we do have some beliefs about how likely we think the null is, and we were going to update those beliefs based on this data. So there's a question about why this isn't, why there isn't p-hacking, which is a very good point. And so so part of the idea here is that so before we run our experiment, we have some prior, that's this p of theta. And so this p of theta shouldn't include any information from our current experiment, right? This is sort of about our prior hypothesis before the experiment was conducted. Then based on that, this hypothesis, we're going to multiply in the evidence from this current experiment, right? And that's going to give us this updated hypotheses, these updated weighting of which hypotheses we think are important. And then we could take this posterior and apply it to a new data set as the prior, right? This can serve as the prior for a new data set. What we wouldn't want to do is take this posterior and plug it back in as the prior for this same experiment. That's going to get us into p-hacking land if we adjust our hypotheses based on the data. And then we go back and multiply that same data as evidence again, right? That's where we're going to get into p-hacking land, right? It's not p-hacking exactly, but that's where we're going to get into like overfitting land, right? Where that data has already gone into our hypotheses and we don't want to add it in a second time. This is actually a kind of a practical problem in the real world, so for example, you might get you hear some piece of evidence in the world and you update your beliefs, and then someone else tells you, oh yeah, I believe that thing too. And you might say, okay, that's even more evidence, but maybe that other person was actually only relying on the same data you were, right? And so you're like double updating your evidence. And so this is like also a practical kind of problem, but yeah, it's the same setup here where we want we want to start with something that hasn't seen the data yet and then add the data in one time. And now we have our hypotheses after data. Okay. So, yeah, so in Bayesian statistics, we usually don't really talk about there being a null hypothesis. There's just hypotheses, and we're going to try to reweight them as we go. And so our evidence that we're getting is going to support each of our hypotheses to some varying degree. And what we want to know is, after we've seen this evidence, how are we adjusting our hypotheses? We actually brought up this issue way back when we first started talking about p-values. I brought up this XKCD example. Right, the idea was that this detector is trying to measure something very unlikely to happen, which is that the sun is exploded. And it rolls 2 dice, and if they come up both sixes, then it gives us a false positive, right? It tells us that the sun has actually exploded. And so the machine says, yes, the sun has exploded. And right, so the frequentist approach here is we don't specify ahead of time whether we think the sun exploding is likely or not, right? We just have our null model, which is that the sun has not exploded. And the probability of this machine saying yes under that assumption is quite small. It's like 2.7%. And so we should reject the null hypothesis and say that the sun has exploded, right? And the piece that's missing here is that before we roll the dice here, we have a pretty strong belief that the sun probably has not exploded, right? And so this evidence we're getting from this machine, it is evidence that the sun has exploded, but it's quite small evidence in comparison to our prior belief, right? So a Bayesian statistician here, right, would say that this probably, right, I agree with you that this is evidence in favor of the sun exploding, but I would still, my hypothesis would be that the sun has not exploded. Right. So the frequentist statistician here doesn't include these prior beliefs at all, right? We just we just assume the null hypothesis is true. We see that this result is unlikely under that null hypothesis, and so we reject the null hypothesis, right? And so that the Bayesian argument is that that's not really a valid thing to do. You really should weigh this evidence against your prior beliefs, and you always have to have some prior beliefs. Okay. So just conceptually, the formula for Bayes' rule is it A, to get a posterior, we multiply evidence times prior. To get a posterior, we add evidence and prior. To get a p-value, we multiply evidence and prior. Or to evaluate our evidence, we multiply our posterior and our prior. Okay, so how do we use Bayes' rule? All right, great. Yep, I'm seeing lots of A's, which is great. And right, the idea here is that we start with our prior, we multiply in some new weighting from our evidence, and then that pops out our posteriors. We don't compute p-values at all in Bayesian statistics. Okay, so let's go through an example. This is actually an example I had in the slides from last year, although it's now become a little bit more relevant. But this is a kind of a classic example of the need to balance our prior beliefs with evidence. So the setup is that there's some relatively rare disease that affects, say, 1% of the population. And so when we say that this is a base rate, what we mean is that this is kind of our assumption. If we don't have any information on a particular person, this would be our guess about the chance that they have this disease. So let's say that there's a new test that's been developed, and this is a really high quality test. So if you have the disease, it will definitely tell you that you have it. It never makes a mistake, which is nice. If you are healthy, then 1% of the time, it'll tell you that you're actually sick, right? So you'll get a positive test result 1% of the time if you're healthy. So this is a great test, right? It never makes a mistake for people that are sick. It occasionally makes a mistake for people that are healthy, but only 1% of the time. Okay, so let's say you take the test and you get a positive outcome, right? The test tells you that it thinks that you're sick. And so the question is, what is the probability that you are actually sick given this test, right? It could be that you're one of these healthy people that has a false positive, right? We're not sure. So what we'd like to do is compute this, right? Given this test result, what's the probability that you actually have the disease? So for to use Bayes' rule, we need two ingredients. We first need to know the prior, which is our base rates in this case, right? Which is that before we took the test, we were pretty sure we didn't have the disease. And we also need to know these conditional rates. We need to know if someone is sick, what's the chance they get a positive? If they're healthy, what's the chance they get a positive, right? And so in this example, we're assuming here that if you're sick, you'll 100% of the time get a positive result. If you're healthy, then just 1% of the time you get a positive result, right? So something to be careful of here, these base rates here are a probability distribution, meaning they need to sum up to 1, right? Like there's some state of the world. We don't know which state the world is in, but it's in one of them. And so our prior distribution is like a real probability distribution that sums to 1. These conditional rates are not a probability distribution. So they don't have to sum up to 1, right? These are occurring in like different worlds. This is in the world where you're sick. Then there's a 100% chance of getting a positive and a 0% chance of getting a negative. In a different world where you're healthy, there's a 1% chance of getting a positive and a 99% chance of getting a negative, right? So these things don't have to sum up to 1. Okay, so these are the two ingredients that we need. So let's try to use Bayes' rule here. So if we try to calculate here, let's say the probability that we're sick given this positive test result, we plug this into our Bayes' rule from a couple slides ago. So you can see here we have on the top here, here's our prior, and here's this conditional probability that if we actually are sick, what's the chance we would get this positive result? So we're just plugging in our numbers. And so we get 0.01 divided by this somewhat mysterious thing in the denominator. Well, I'll show in a second here how to actually calculate this, right? This in the denominator is what's the probability of getting a positive test result in general, right? If we test everyone in the world, what fraction of them are going to get positive test results? So I'll show how to calculate that in just a second. Usually the easiest way to calculate this actually is that we just look across all of our possible hypotheses about the world. So one hypothesis is that we're sick. The other hypothesis is that we're healthy, right? What's the probability that we're healthy given that we got this test result? We just plug into our formula again here, right? We have our prior, which is 0.99, our conditional probability of 0.01. And so we end up with this 0.0099 thing. And so a trick we can use to figure out what this normalization constant thing on the bottom here is that these two probabilities have to add up to 1, right? Given this positive test result, either we're sick or we're healthy. These are the only two possibilities, and they're mutually exclusive. So what that tells us is that the sum of these two things has to equal 1, right? And so this is actually usually the way that we work out this denominator piece here, right? Is we just figure out how we could set this so that the sum of all our hypotheses equals to 1. Right. You could also think about what's going on here, right? Is what this is telling us is that about 2% of people in the world are going to test positive. 1% of them are the sick people that are all testing positive, and the other 1% are the healthy people that are getting false positives, right? So the overall positive rate is like about 2%. So if we just plug this into our fractions here, right, what we end up with is the probability that we're sick given this positive test result is about 50%, right? So this is, now that we've run this result, it's basically about a 50-50 chance that that we are sick based on this result. And so the reason this is often used as an example is because it's pretty most people's intuition is not this, right? If you hear that this test only has a 1% false positive rate, then when you take the test and you see a positive, you might think that that means you have a 99% chance of having the disease, right? But this is not really true, right? That we have to combine our prior belief, which is that this belief is that this disease is quite rare, with this positive test that we got, right? Which is that this positive result is way more likely among sick people than healthy people. And so Bayes' rule basically lets us combine these two things. And in this case, these two things kind of cancel out, right? And it says that it's about equally likely that you're sick or healthy here, right? And so that's why it's important that we don't just use the data, meaning these conditional probabilities, that we also take into account these base rates. So just to try to get some more intuition for what's going on here, right? Right. Again, it seems kind of weird that a test that's only making mistakes 1% of the time is going to be a false positive half the time. And right, we have to, the key here is that there's lots of healthy people in the population. And so false positives actually happen quite frequently. So you can imagine right here are 1,000 people. The blue squares are healthy people and the red squares are sick. And so right, 99% of the right, so 99% of the squares here are blue. Yeah, well, maybe we don't have quite that many squares. Maybe we do. Right, the point is almost all these squares are blue. There's a rare disease that only a small number of people have. So now all of these people take their test. For the people that are sick, 100% of them are going to get a positive result, and 1% of the blues are going to get a positive result. And so the shaded in squares here are these people that are getting positive results, right? So you can see all of the people that were sick got a positive, and 1% of these healthy people got a positive, right? And so what you can see here is that, right, if you tested positive, you're either one of these red squares here that are always diagnosed, or you just happen to be one of these 10 sort of unlucky blue squares, right, that happen to get a false positive, right? And so based on getting this positive, you know that you're in this group here, which is about half healthy people and half sick people, right? So again, what's happening here is that the test is quite accurate, but the prior probability that you have the disease is so low that that even after the test, you're actually quite unsure which of these groups you're in. So how do we actually solve this in like medical situations? There's a few ways to deal with this. A common thing is that we can simply think about running a second test. Right now, we don't want this test to be correlated with the first test. That's not going to help us if it just returns a false positive for the same people that the first test did. But let's say there's something else. There's like some other biomarker we can test. And let's imagine the second test is like actually not even that good. It's right only if you actually are sick, then you only have an 80% chance of getting a positive. If you're healthy, then 10% of the time you're getting a positive. Right. So this test is way worse than the first test. It's missing sick people and it's misclassifying way more healthy people. But let's imagine that we ran our first test and then now we're running this second, not that great test. So how should we update our beliefs? So let's imagine, right, we get a positive again on the second test. And so what we're going to use here is, instead of our prior now is not the base rate. Our prior is our outcome from the first experiment here, right, which is about 50-50. And then we now have these new conditional rates for this new test 2. And so the probability that you're sick if you get a positive on test 1 and test 2 is we take these, our prior rates, right, and then we're going to reweight them by these conditional. And I've skipped some of the math here, right, but now this comes out to about 90%, right? So if you get getting a positive from the first test raises your chance of being sick to 50%. Getting a positive for the second chance moves it all the way up to 90%, right? And so this, now you should be much more concerned about seeking treatment for this. And so, right, this is why for rare diseases, right, we almost always want to run multiple tests, right, multiple uncorrelated tests. The tests don't even have to be all that good, but we can just accumulate information across them, right? And we can build up our beliefs here. If we're for a rare disease, the starting point assumption is that it's very unlikely we have this. And so we're going to need to see multiple strong pieces of evidence in order to downweight that prior belief. Right. And so, again, this understanding of base rates tends to be pretty unintuitive for people. And the specific outcome, which is that for rare diseases, most positive test results are going to be false, right? Even if the tests are pretty good, most positive test results are going to be false positives, just because there's many more healthy people than sick people. But if we have two independent tests, and again, it's important here that the tests are not correlated with each other, that this is a new piece of information that we're getting, then we get a lot of value from having this extra test. Even if it's kind of a mediocre test, it's really helpful because we can accumulate information across these tests. There's even certain kinds of like statistical models. There's a whole family of statistical models called boosting, which is basically trying to get a very large number of mediocre models and putting them all together. And we'll talk about this a little bit on Thursday too. And so there's a question here about what if we don't know the base rate? And this is sort of the big hurdle with Bayesian statistics. And the reason that it's still not as commonly used is that you have to specify some base rate. And so in a lot of medical cases, we sort of know. We certainly don't always know, especially for conditions that are relatively recent. We don't know. You could also imagine, like in the case when we're using this to test hypotheses, right? What's the prior probability of like some certain social psychology hypothesis or something, right? And it gets a little bit tricky because it requires you to actually write down what you think the probability is. It might require you, if you're putting this in a paper, it might require you to defend that against people that disagree with that prior, right? And so this is it's a little bit tricky because the whole point is that this prior doesn't depend on the data you're currently collecting. One thing we can do, and we'll show this in an example in a few slides, is at least in some cases, you could kind of assume that everything is equally likely. So you could start out with what's called an uninformative prior, which is just that we think all of the outcomes are equally likely. So we think that every possible value of the population mean is equally likely, for example. And that makes sense, at least in some situations where the population parameter is bounded. But in other situations where the population parameter could take any value from like 0 to infinity, then it's a little less clear how you would write down that kind of distribution. So yeah, so this is a big stumbling block. We'll come back to in a few different ways. Okay, so how do we actually connect this to stuff we care about in statistics, right? Is that, right, this seems like a somewhat disconnected example, right? But the idea here is we're going to use the same kind of logic, which is that we want to be able to draw conclusions from measurements, right? And so what we're going to want is to write down our uncertainty about a hypothesis about how the world works. And we're going to want to collect data from an experiment that can distinguish between these different hypotheses. And that can help us reweight our beliefs about the world. Right. So there's also a kind of element of experimental design in here that we want experiments so that the evidence can tell us which of these hypotheses are true. Right. We want to have data for which different hypotheses are going to make different predictions. Okay. Let's do a quiz to sum up this part. So if there's a test that that from sick people that, right, if you're sick, the chance of getting a positive result is 85%. And if you get a positive result, that means that there's an 85% chance you're sick. There's a 15% chance you're sick. You are definitely sick, or we don't know. Right, so what could we conclude from this? Yeah, so the answer is we don't know. Actually, we need to know not only P sick, we actually also need to know the other conditionals. We also need to know what's the chance of getting a positive if you're healthy, right? So so this, just knowing this one conditional rate doesn't really tell you anything about what a positive means. Okay. So the somewhat confusing thing here that was also a stumbling block to using these methods for a number of years is that we often think here about not just like a countable number of hypotheses, and like we have a single null and a single alternative, but we usually think about full distributions, meaning that there's sort of an infinite number of models that all have very slightly different population means. And so, for example, one challenge here is like actually computing these things in realistic spaces. So our prior starts out as a distribution that reports the probability of every possible state of the world, and so does the posterior. And so what we're going to get out at the end here is not like a single value. We're going to get out a whole distribution over values. And this is a good thing, right? This is sort of like a confidence interval. The interpretation is maybe slightly different, but than a frequentist confidence interval. But right, we're going to end up with this distribution over how probable we think it is that the population parameter has all of these possible values. Right, we've already been talking about confidence intervals kind of like this, right? That when we end up with a confidence interval, we're saying that this single X bar, for example, right, the mean in our sample is my best guess, but it's not my only guess of what we think the population mean is. We need to really look at this whole confidence interval, right? So frequentist confidence intervals are maybe slightly different, right? We talked about this, that they a 95% confidence interval basically means that you captured the correct mean 95% of the time, which is a little bit of a convoluted probabilistic statement. These Bayesian estimates are like a little more intuitive, right? They're going to give us a distribution about the likelihood that we think we have a sample mean of all of these possible values. Okay, so let's work out an example with a coin. And so what we're trying to do in this experiment is figure out what is, for this particular coin, what is its weighting? So what's the probability of getting heads on this coin? And so we're gonna imagine we're gonna like spin the coin to make it slightly more interesting, and we're gonna try to figure out whether this coin is fair or not. Meaning, what we want to figure out is this P of H close to 0.5 or not. So here we have we don't just have a single like null and alternative model. We have a sort of an infinite number of models ranging from pH equals 0 up to pH equals 1. And so we need to start with a prior distribution, right? Which is before we've collected any data, what do we think the chance is that this coin has each of these possible P of H values? And then we need a likelihood function, which is going to serve as the way we're going to evaluate our evidence, right? This likelihood is the same as these conditional probabilities I've been talking about. That will help us every time we see a particular sample of this coin, how should we update our distribution over this 0, 1 distribution. Okay, so we need to start with a prior distribution. This is, again, is a continuous parameter from 0 to 1. And so the area under this curve, just like for all our probability distributions, tells us the relative odds of each of these possible intervals, right? And so the idea is that if we make this distribution higher in some places, it means that we think it's more likely that P of H is around that value. So we could start off with just a naive prior or an uninformative prior, which is that we think every possible value is equally likely, right? This is just a uniform distribution between 0 and 1 that says before we've collected any data, we think that it's just as likely that the probability of heads is 0.2, that it is 0.5, that it is 0.9, or that it's 1, right? So this is something we can try to do if we don't have a good idea of our prior. It doesn't always make the most sense. I mean, in this case, this is maybe not the most sensible prior because most coins in the world probably are fair or close to fair, right? So the chance of getting a coin that has pH of 0.1 is probably way less likely than a pH of 0.5 or something, right? But here we're just, maybe we're very suspicious of this coin for some other reasons, right? The reason we're testing this coin is because we think it's suspicious. And so we're just going to say we don't know what's going on with it. Okay, so that's our prior. Then what we need is we need these conditional probabilities for that middle piece of Bayes' rule, which is for every possible value of P of H, then what is the chance of getting what's the chance that our data would look a particular way? So this is also a continuous likelihood function because we have to be able to, we sort of need like one of these functions for every possible value of P of H. And so in our case, this likelihood function is easy because we're just getting, our data is just a single outcome here. And so if our, the probability of getting heads here is just P of H, right? So what this tells us is that if this coin, if the true P of H of this coin is 0.1, then we'd expect to see heads if the true P of H here is like 10%, then we'd expect to see get heads like 10% of the time, right? So this is a likelihood function, which is telling us that for each of these, this x-axis here is like all of our possible worlds. We don't know which one we're in, but the pH of our coin is one of these things. And in each of these worlds, there's a different chance of getting a heads on a single trial, right? If pH is 0, then there's no chance we're going to get heads all the way up to pH of 1. We could also get tails on a trial, right? And that's just the opposite curve here, which is that if pH is 0, then we're always going to get tails, right? So these are the two ingredients that we need for doing Bayes analysis, right? We need to say what our starting distribution is, and then we need to say how our data should look under each of these possible worlds. And so what this tells us is that if we're in the world where pH is really high, we should get almost all heads and very little tails, and vice versa. So here's our Bayes rule here, where we've just plugged in these things. So the population parameter we care about here is this pH, the probability of heads. And what we want to know is after we've seen our data, which is just a single, just going to be a single sample for now. So after we've seen our data, this single coin, how should we update this probability distribution? And so remember our ingredients here. Here's our prior. So before we flip the coin, what do we think the likelihood is of each of these possible outcomes? These are going to be our little evidence functions, right? Which is under all of the different possible settings for P of H, how likely is it that we would have gotten this data? And all we need to do is just multiply these things together. So these things are now not numbers, they're actually distributions, right? This is not just a single model we're looking at. This is there's a right, and it's not just two outcomes like healthy or sick. There's just a continuous set of outcomes for P of H between 0 and 1. And so we're just going to multiply. When we say pointwise multiplication, what that means is we just line up the distributions and just multiply the points that are at the same values of P of H. So let's see what happens when we get our first, we're spinning our coin, we get our first value, it's heads. And so what Bayes' rule tells us is we take our prior, which is this flat thing here, and then we multiply in our evidence, our likelihood function for heads, right? And so remember what we said here is that if P of H is high, then we would expect heads. If P of H is low, then we don't expect heads. So we multiply these things together, and then we end up with our posterior. So now I'm noting here this is an unscaled posterior because I'm ignoring this term in the denominator. This term in the denominator doesn't depend on P of H. It's just going to be some overall scaling. So we can often ignore this thing. We're gonna talk more about this thing on Thursday too. But right, so the pieces here is that we start with our prior. Based on our data, we can say how likely is it that we would have gotten this data under each of these possible hypotheses, and then we have our posterior after a single flip, right? So after a single flip of seeing heads, we're definitely sure that this is not, that P of H can't be 0, right? We're definitely sure that this coin doesn't only produce tails because we saw a head, and we think it's more likely this is like a coin that prefers heads than tails, but we're not really sure. We're not 100% sure, right? That we still have a distribution here. So let's see what happens if we actually do this a bunch of times. So here is a little simulator of this. Okay. Sorry. Okay. So, right. So let's do this same example here. So we have a coin. We're going to start out with just this random guess here. We don't know what whether the coin is fair or not. We're just going to say it's equally likely that P of H is between 0 and 1. And so let's say that the true P of H here is like 0.2. Okay. So this dotted line here is the true value of the population parameter. So let's flip the coin one time and update our distribution. So we flipped the coin once and we got heads. And so, right, what happened is that we multiplied our prior by this, this likelihood function for heads. And what this tells us is that we're definitely sure this is not an only tails coin. And we think it's probably a heads producing coin, right? You can see we're actually wrong about that, right? The true population parameter is this one, is 0.2, right? But we're also not, this distribution is not really that sure, right? You can see the area is pretty spread out here. Okay, let's flip the coin again. Now that time we got a tails. And so what we did is we took our current belief, which was this straight line, and multiplied in the likelihood of tails, which was a line that was sloping in the opposite direction. Right, and so now that we've seen a heads and a tails, now our belief looks like this, which is we're definitely sure this coin doesn't produce only tails. We're definitely sure it doesn't produce only heads. It's probably somewhere in the middle, right? You can see we're pretty, this curve is kind of flat, meaning we're not really sure, but it's like probably somewhere around 0.5. It's like very unlikely that it's all the way in the corners here. All right, let's flip the coin again. There we got another heads. And so you can see now what we did is we took our distribution, we multiplied it by a straight line going left to right here. And so it's kind of smushing our distribution a little bit, where now we're starting to think P maybe is somewhere around 0.7, but we're still pretty unsure, right? It's still possible it's over here somewhere. And again, the true value is here. So you can see every time as we collect more data, the probability of this true outcome, which is the height of the line at this true outcome, doesn't always go up. Right? Sometimes we see evidence that actually looks like something else, right? So far we've gotten 2 heads and a tail. And so our estimate of this, our beliefs here don't have to always increase on the true belief, right? But over time we should get closer and closer, right? So let's start flipping more coins. Let's do we're gonna do 10 flips now and multiply in our evidence. So you can see after 10 flips, in those 10 flips, we got a lot of tails. Right? It looks like actually maybe almost all of those 10 were tails. And so every time we got one of those tails, it shifted our beliefs here. So you can see a couple things happening. First of all, as we collect more and more data, on average, our the height here at the true p is going to go up, right? On average, we should be assigning higher and higher probability to the true model, which is this p of 0.2. You can also see that our probability distribution is getting a lot tighter, right? That now we are quite sure that it's somewhere between like 0.01 and 0.4 or something, right? That we're quite sure it's somewhere in this range. We think it's really unlikely that it's out here. It could be, but we've gotten way too many tails for this to be likely, right? And so as we're collecting more and more data, we are, at least on average, the probability of the true model is increasing, right? Not on every step, but on average. And this distribution is getting tighter and tighter. So if we keep flipping, let's keep flipping tons and tons of coins. And you can see this distribution kind of wiggles around over time. But eventually it's getting really close to the true answer, right? And it's getting tighter and tighter and tighter, so that, right, you can see what's happening here is our most likely estimate is not quite right. Our most likely estimate is like 0.25 or something here. But we're like really sure it's somewhere in this range, which is between maybe 0.1 and 0.3 or something, right? So the range here is getting tighter and tighter. And so this is the idea with these Bayesian updates, is that as we get more and more evidence, our distribution over our beliefs here should hopefully get more and more certain, right? That we can start discarding. At this point, we've essentially discarded these hypotheses, right? We never actually remove hypotheses from the pool, but these ones basically cannot be rescued at this point, right? They're close to zero probability. And so we're quite sure about where we are here. And so this does also depend, right, to some extent on the prior. I mean, with enough evidence, it'll kind of wash out the effects of our prior, right? With enough evidence, then what our prior belief was will matter a lot less. But at least for small experiments, the prior can matter a lot. So let's imagine that, let's say our prior looks something like this. Let's try to set it to like, yeah, what these alpha and beta means is not super important. They're just controlling the shape of this prior. So here's a prior where this prior is that we think it's likely that this coin is close to fair, and we think it's definitely we're 100% sure that it's not a tail only or a heads only producing coin. But we think our prior belief here, before we've seen any evidence, is that we think it's probably close to fair, but we're not sure. Right, and so then let's see if we do a single flip here. Right, so we can see we get a single flip of tails was our outcome. And so we combine that with our prior, and now this is our distribution here. Right, and so again, no matter what our prior is, with enough samples, we will eventually converge onto the right answer here. We'll eventually kind of ignore whatever that prior was because we've seen so much evidence, right? But usually in experiments, that's not the case. Usually in experiments, our evidence is not that strong that our prior usually does make some difference. But right, this is also another way, if we are worried about that we really don't have a good prior, is the answer is, right, try to collect lots and lots of evidence so that the way you set your prior is not that important. Okay, let's do one more quiz on this section. So as we're collecting more and more data and we're running this Bayesian updating process, the probability that we assign to the true value that we don't know, right, what the true value is, but the probability we assign to this true value of the population parameter, A is going to always increase with every data point. B will always just stay the value that it has in the prior. C will randomly increase or decrease with equal likelihood, or D will increase toward 1 on average. Okay, so yeah, so how should we expect the probability that we assign to the true state of the world? How should that change over time? So yeah, so some let's see. Oh yeah, so I'm seeing a few D's here, right? Which is the correct answer is that as we collect evidence, our evidence should be most consistent with the true state of the world, right? Because that's where our data is actually coming from, is the true state of the world. And so on average, our evidence should be most consistent with the true state of the world. And so as we get more and more evidence, we're going to, the correct answer here is D, is that we're going to increase toward 1 on average, right? That as we get more and more evidence, the probability of this true value is going to go up on average. But it's not, the answer is not A here. It's not that every data point is going to help us, right? Sometimes we'll get samples that actually look like they're coming from a different world, a different state of the world, right? This is just basically the whole part of the whole reason we have to do statistics on this, is that sometimes our samples are misleading, right? An individual sample might be misleading. But it's not equally likely to increase or decrease, right? Most of the samples we get should look consistent with the way the world actually is. And so, right, so when we were running our little simulations here, right, what this means is that as we flip the coins, let's say here the true value is a half, right? This is a fair coin. As we flip the coin more and more, right, the height of our distribution that's at this purple line here, right, that height should keep going up and up and up, right, until eventually, well, for continuous probability, we can never really get to 1 exactly, because we can't be infinitely skinny here, but right, eventually we basically should have our entire probability distribution centered on this one single true hypothesis. Right, and that's because that is the world that's actually generating our data. And so with enough data, we should be able to figure out which world we're in. Okay, so let's do another interactive example of this. So this example is based on a real event, which was that there was a nuclear submarine, the USS Scorpion, which disappeared in 1968. And it was returning to base, and even to this day, we don't know exactly what happened to it, why it sunk, but it suddenly just we lost all communication with it. And so we wanted to try to, the US Navy wanted to try to search for the submarine. And so they didn't know exactly where it was, but they had some guess about where it was likely to be. So they had a this prior distribution over where they thought it might have been, and then they wanted to conduct a methodical search. And so what they did is they did this using a Bayesian approach, where what they did is they started from this prior, their guess about where the ship might be, and every time they took a measurement, they would update their beliefs about where the ship might be. And so this is a little simulation of this. This is a simplified version that has 9 squares instead of 400. But so the logic of this is so we'll hit start here. So here's our prior guess about where we think the submarine is. And so the color of these squares indicates the strength of our prior. So what this is saying is that we're pretty sure the submarine went down somewhere over here. I don't know if you can read these, but if you click on the squares here, it tells you, these 2 squares have something like a 16% probability. This square over here is like an 8% probability, right? So before we've even started searching, just based on the path of the submarine, we have a rough idea that we think it's somewhere over here. Maybe it was on one of these squares. We don't think it's over here, but we're not sure. So now what we're going to do is we're going to take our little search vessel, and we're going to try to start looking for the submarine. And so one question is, where should we start? And so the strategy they took is that you should just always search at the most probable space, right? So here, the most probable location based on our current beliefs is this middle square here. So we're going to drive the ship over here, and then we're going to search for the submarine. And so searching is pretty hard. And so if we find the submarine, then we are done. We found it, and we definitely know where it is because we found it. If we don't find it, then we're not really sure. It's maybe we just missed it because it's really hard to find, right? And so let's do a search. And so we did our search, and we didn't find anything. And so we're not really sure if it's there or not, right? And so let's do one more search here. So we did another search. We still didn't find anything. And so it could be that we missed it twice, but you can see the probability here now in the square has sunk down to 7%, right? We've updated our beliefs based on this evidence, and the evidence isn't 100% compelling. It's possible we missed it, right? But we searched for a couple of days in this square and we didn't find anything. And so this square is now becoming less likely in our distribution. You can see as we're searching, the probabilities in other squares can change, and that's mostly just to do with the way this is being normalized, right? Which is that if this square becomes less likely, then this square here, for example, becomes more likely. So this one went from like 15% to 17% because we know that it's not here. So that makes it more likely maybe it's here instead. So let's go here and search a little bit. Okay, yeah, we didn't find anything. So we spent a little time searching here. We didn't find anything. Maybe we missed it, but now we think there's only like an 8% chance it's in this square. Right, and so this is the way they actually conducted the search. Is they had some rough statistical model of how likely it is they thought their search would fail. They went through this process of searching around to the most probable locations. One thing that's not accounted for in this simulation is it takes time to drive between these squares. So, for example, right now the optimal square to search in is over here, but that's kind of far away. Maybe we should actually just search here while we're in the neighborhood. Right, so eventually we can sort of narrow down. Okay, so it says I found it, right? We eventually found it in the square here, right? And so the idea is that we'd want to have some set of beliefs over where we think things are. Every time we get some evidence, we're going to reweight those beliefs. And doing this requires us to have both some kind of way of writing down a distribution of our prior belief. And we also need a way to, we need some model of what we think our likelihood functions are, right? So in this case, we need to know like what we think the chance is of not finding the submarine if it's really at this location, right? If we search in a location and we don't find it, what does that tell us, right? What's the probability that the submarine is there and we don't see it? And so those are, again, the kind of things we try to estimate in a Bayesian model. We might do some kind of controlled testing to figure that out. We might also just have to sort of plug in estimates of these things. Okay, so I wanted to just do one other quick example here. And this is an example from my research. And so I've run experiments where we have people watch a movie. So they, for example, watch the first episode of the BBC Sherlock series. And then they try to retell the movie from start to finish. And while they're doing this, both the watching and the recalling, we're measuring brain activity using fMRI. And so I'm interested here specifically in this recall part. So people are trying to remember the movie and tell it back to me. And so let's imagine that the subject has just talked about scene 19 out of the 35 scenes in this movie. And I want to see, just by looking at what their brain looks like right now, can we estimate what scene of the movie they're currently talking about? Right. So I'm measuring brain activity, which we're basically trying to see is is their brain activity, does it tell us something about what they're currently thinking about and talking about? We want to figure out, can we estimate what scene of the movie they're currently talking about by looking at their brain? And so I'm doing this in a Bayesian way because even before I look at their brain activity, the fact that they just finished talking about scene 19 gives me some guesses about what they're going to talk about next. So before I even look at the brain activity, is that they're probably going to talk about scene 20 next. I mean, they might not. People also skip scenes. So they're probably good. I think there's an 80% chance they're going to talk about scene 20. There's a 15% chance they're going to talk about one of the later scenes. So there's a 1% chance on each of those. And there's some tiny chance they're going to double back to some earlier scene and say something out of order. Right. So we have some prior, which is that we think they're probably going to talk about scene 20, but we don't really, it could be something else, right? There's some low chance they're talking about, they're going to skip scenes, and there's some even lower chance that they're going to talk about something from the past. So we have our prior, then we have our evidence, right? Well, we have to write down some kind of likelihood function that says, if they were talking about scene 20, what would their brain look like? And so all we're doing here is this R is just a Pearson correlation, right? What I'm doing is I have a kind of template pattern of what people's brains look like during each scene of the movie. And then I'm measuring the current pattern when they're speaking right now, when they're doing the recall. And so our hypothesis here, this is not actually an equal sign, there's some other terms here, but is that if they're talking about scene 20, their brain should look like it did during scene 20 of the movie when they were watching the movie, right? If they're talking about scene 21, their brain should look like it looked during scene 21 of the movie. So we have this prior and this evidence, and so we can combine these two to get an estimate of which thing they're currently talking about, right? And so the fMRI activity on its own is quite noisy. So this evidence is quite noisy, especially from like any particular sample we get. And so this prior can really help us a lot, right? This prior is basically saying people usually talk about things in order without skipping scenes. They sometimes skip scenes, and very rarely they'll sometimes go back in time, but usually they're kind of talking about things in order. And so this prior helps us a lot, that even if this evidence is kind of fuzzy, we can still keep track of where people are, right? Even if we kind of lose them for a few seconds, we can get back on track by using this prior. So I'm going to show an example of this kind of tracking. I'm going to play the audio for this. This is audio that's recorded from inside the scanner while they're talking, so it's quite noisy. You might just want to turn down your volume if it hurts your ears, because it's like kind of squeaky. You can also, I have the text on the screen of what they're actually saying. But so this is just a short clip of someone. They're talking about in this experiment we actually showed people a number of different stories. So here it's showing 8 different stories. And their job was to recall one of them. And we're trying to figure out which one they're talking about and which part of the story they're talking about. So the dotted square here is going to show the correct answer. So the story that they actually are talking about is this clip from the movie Brazil. And the dotted line here, they're going to start in this what they're actually talking about is this first scene of Brazil. And then they're going to proceed through the second, third, and fourth scenes of this clip. The colors in this square here are the posterior probabilities from our Bayesian model. So things that are yellow here is where the model thinks the person currently is, what it thinks the current person is currently talking about, right? And it's not using what they're saying at all. It's only using their brain activity, and it's using this prior. And the prior in this case is people are going to talk about only one of the stories. We're not sure which one it is, but they're only talking about one of them. And we think they're going to tell the story roughly in order. Okay, so I'm going to play this example. Again, if the audio is annoying to you, you can just turn it down for a minute.
Is wearing like all cheetah print and has like a cheetah print stiletto on her head. Goes to a French restaurant with her son and meets up with some of her older friends. And they're all dressed really weird and have a lot of colors on. And her son really wants to talk to her, but she's ignoring him. And they're all ordering on a menu, and it's like an electronic menu. And the waiter forces the son to order steak. And then when it comes, it's like these green circular entrees. And the son's still trying to talk to the mom, but the mom's talking to her friend about her like Botox treatment or something. And they're talking about different surgeons. And they begin eating.
So anyway, this is just an example of a way we can try to use this approach where we have some kind of like noisy, unreliable data, and we can clean it up by applying these priors, right? By leveraging these priors and combining our evidence with the priors, right? What we're also doing here is combining evidence over time, right? We're getting repeated measurements of this part of people's brain. And so even if some of these measurements are bad, later ones are better, right? And so by combining evidence across time points, we can do a pretty good job of figuring out what people are thinking. Okay, so just to sum up, right, from things we've talked about today is that, first of all, understanding these issue of base rates, and this is referred to as a base rate fallacy, that people tend to not incorporate base rates, right, that even reliable tests can yield many false results if the base rates are that most people are healthy. Right, and we talked about this concept of Bayesian updating, right? And again, you could think about lots of applications of this, right? Of how we can combine priors about the world with evidence to make conclusions about how we think the world actually works. So in the next lecture, we're going to talk about a few extensions of this. We're going to revisit this denominator constant, which was somewhat mysterious today. And in fact, you can actually use it for doing lots of interesting things like getting support for the null hypothesis or for comparing different models. So to sum up, this Bayesian statistics approach, right, is a different way of thinking about statistics with a different goal, that instead of deciding to reject or fail to reject a null hypothesis, we're instead going to have some distribution of beliefs over potential hypotheses. It uses this. It starts with a prior belief and updates this belief over time, and is just concerned with the weight of the evidence in just a continuous way. And so the procedure is a little bit more mathematical, but right, it is just founded in the rules of probability theory. And when we're using these entire distributions, we're ending up with the end goal here is that we get these posterior distributions. And so, right, once again, we're basically the high level goal here is the same as what we've been doing throughout the whole class, which is that we want to say something about where we think the population parameters live, right? What's the actual state of the world and how confident are we about it? All right, so on Thursday, we're going to do a second half of more Bayesian stuff. Any last questions for today? All right, thanks everyone. Office hours are going on as normal this week, so feel free to tune into mine tomorrow if you have additional questions, and I'll see everyone on Thursday.